The majority of stars in the universe are red dwarfs. So, how habitable these systems are is a key question in the field of astrobiology. In fact, 6% of all red dwarf stars seem to have Earth-sized planets in their habitable zone. Of all the stars that can fuse hydrogen, red or M dwarfs are the smallest and have the lowest luminosity. Generally, main sequence stars with a mass between 60 and 8% the mass of the Sun are considered red dwarfs. When the mass of a star is decreased, the luminosity will also decrease, but not in a linear manner. If the star is smaller, the lower gravity will decrease the pressure in the core of the star, causing each kilogram of material to fuse hydrogen at a lower rate. As such, the luminosity will decrease faster than the mass will. For example, in order for a planet orbiting a red dwarf star with 8% the mass of the Sun to receive the same total insolation it has on Earth, it would have to be 0.0262 astronomic units from the star, while a planet orbiting a red dwarf star with 43% the mass of the Sun would have to be 0.181 astronomic units to receive this much insolation. This means that if a planet was close enough to a red dwarf star for the light emissions to sustain liquid water on the surface, the planet would be tidally locked, with one side constantly facing the star. So, one side will be in perpetual daylight, while the other side will be in a permanent night. This has led to speculation that an atmosphere wouldn't persist on such a planet, because the night side would be so cold that the atmosphere will progressively freeze out on it. However, atmospheric modeling has indicated that circulation could provide enough heat to the dark side to prevent the atmosphere from collapsing. Another problem with atmospheric retention on such a planet is the intensity of the solar wind that close to the star. While intuition would state that with a cooler surface, less energized particles would be produced, the gravity of the star would also be less, so it would be easier for ionized particles to escape. This is further compounded by the tumultuous interior of red dwarfs, which can bring many high-energy particles from deep down closer to the surface. The majority of astrophysicists would argue that the intensity of the solar wind in the habitable zone of a red dwarf star is more powerful than what we experience in the habitable zone of our own Sun. However, there are still many as of yet unquantified factors that determine the intensity of a star's stellar wind, so the question is far from settled. Although one thing that could compound this problem is the predicted strength of a magnetic field of a planet that orbits a red dwarf. Earth's magnetic field shields the atmosphere from the solar wind, and what keeps the magnetic field active is known as the dynamo effect. This is where the rotation of the Earth keeps the liquid iron outer core moving, and thus induces electric currents, which in turn generate a magnetic field. Since any planet orbiting a red dwarf would rotate much slower than the Earth, i.e. at the same rate that the planet revolves, there wouldn't be as much fluid motion in the core, and it would likely have a weaker magnetic field. Although, there are many factors that influence the strength of the magnetic field of a planetary body, some well understood, others not so much. So, while the average magnetic field strength of planets in the habitable zone of red dwarfs would be less than that of Earth, it isn't inconceivable that some could have a field that is of the same strength or even stronger. Furthermore, Venus lacks a strong magnetic field, yet still has an atmosphere far thicker than Earth's. As such, if a planet had strong gravity and an atmosphere composed mostly of oxidized gases, it could maintain a thick atmosphere even with a weak magnetic field while being subjected to stronger solar winds. While our current understanding of astrophysics suggests that atmospheric retention is more difficult in the habitable zones of red dwarf stars, it far from rules out the possibility that some of these planets could keep their atmospheres. So, how would the trajectory of early life on a planet orbiting a red dwarf star compare and contrast to that of early Earth? Well, for one, the two planets would be dealing with a temperamental sun. Virtually all red dwarfs are flare stars, meaning that their luminosity can vary by up to 40% and will produce sudden intense bursts of ultraviolet light, and in the first billion years of their life cycle, G-type stars such as the Sun exhibit similar behavior. Now, it's generally believed that the first organisms on Earth lived in hydrothermal systems. Here, They may have taken up abiotically produced organic molecules or reacted hydrogen emitted from the vent with atmospheric carbon dioxide to generate its own organic molecules and produce energy. One early metabolic innovation was likely the use of various sulfur-based molecules as electron acceptors to oxidize either hydrogen or organic molecules, giving rise to respiration. But then around 3.5 billion years ago, we find the oldest evidence of photosynthetic organisms, and this is where the course of evolution on a red dwarf planet likely took a very different turn. While the Earth's sun calmed down, red dwarfs remain highly variable, releasing sudden bursts of UV light to this day. This would expose any photosynthetic organisms to deadly ultraviolet radiation. Furthermore, while a planet in the habitable zone would be getting as much light energy as the Earth does from the sun, there is a qualitative difference which can make photosynthesis problematic. In order for an electron to be stripped from an inorganic molecule to reduce carbon dioxide to an organic molecule, it has to be struck by a photon with enough energy. The shorter the wavelength of a photon, the more energy it will have, and photosynthetic organisms typically use photons with wavelengths between 700 and 400 nanometers. This range is known as photosynthetically active radiation, or PAR, which comprises roughly 12% of the light energy emitted by the sun. Since red dwarf stars have cooler surfaces than the sun, they will not only produce less light per given area of surface, but the average wavelength of the photons will be longer. As a result, a smaller percentage of the light emitted will be PAR. In the hottest red dwarfs, half as much light is PAR relative to the total emission of the star, while in the coolest, it's 1/12 that of the sun. Now, it should be noted that there are a wide range of environmental variables which limit photosynthesis, such as the availability of water, nitrogen, phosphorus, potassium, or iron. So, if the availability of PAR was cut by 50%, global photosynthesis could potentially still occur at 75% the rate that it does currently. But as you further decrease the availability of PAR, the more and more it will be the limiting factor. So at 25%, global photosynthesis might be 30% of what it is now, and at 15% it would be 16% as you approach a linear relationship between the percent decrease in PAR and the percent decrease in photosynthesis. So, ignoring the flare activity for now, the hottest red dwarfs could probably sustain well over half the photosynthesis we see on Earth, while the coolest could only support 1/12. The availability of PAR would also likely impact the evolutionary trajectory of photosynthesis. Even though the overwhelming majority of photosynthetic organisms on Earth today use water as the electron donor, the earliest used hydrogen sulfide. Since oxygen is more electronegative and it clings onto electrons more tightly, the bonds in a water molecule will require more energy to be broken than those in a hydrogen sulfide molecule, i.e., the photon would have to have a shorter wavelength. This means oxygen producing or oxygenic photosynthesis would be more impeded on a red dwarf planet than anoxygenic photosynthesis. So while the first photosynthetic organisms evolved 500 million years after the first life on Earth, and oxygenic phototrophs evolved 700 million years later, on a red dwarf planet, one might expect the first photosynthetic organisms to appear 600 million years after the first organism, and the first ones to produce oxygen to come about a billion years later. But there's still the problem of the sudden and intense flares of ultraviolet radiation. Thankfully, water absorbs UV light far more readily than PAR. So, if photosynthetic organisms form microbial mats 5 to 10 meters deep, they could carry out photosynthesis without suffering from a lethal dose of radiation. One advantage these organisms would have over the first phototrophs on Earth is that they wouldn't have to deal with tides, which would bring them in contact with intense UV light at low tide, forcing them to go dormant during this time. Although enormous waves resulting from the high winds could bring them in direct contact with intense UV light during a flare, and it would do so in a matter of seconds versus hours, denying them the time that they need to enact photoprotective measures. So, it may be that photosynthetic mats could only grow in areas where the wind was blocked by nearby coastal terrain features such as mountains. While single-celled phototrophs couldn't live near the surface, multicellular algae-like organisms could employ some strategies. For one, they could form a small flower-like structure with photosynthetic cells on the top side of the petals, UV-absorbing pigments on the bottom side, and a UV light receptor on top of the stigma. When the light receptor begins to detect an increase in UV light at the start of a flare, the petals, or leaves if you want to call them that, would close up, shielding the photosynthetic cells. When the flare resides, the flower would open up and photosynthesis would resume. This could then allow photosynthetic organisms to colonize the land. But once here, they'll face more troubles than the UV light. As I mentioned before, it's been hypothesized that atmospheric circulation could keep the atmosphere from freezing out on the dark side. Air around the point of the planet closest to the star, or substellar point, would be heated, rise, and flow over to the night side in the upper atmosphere. Once there, it will cool down and sink opposite to the substellar point. Next, it will flow over to the day side along the surface until it nears the substellar point, where it gets heated, rises, and the cycle repeats. What would this mean for the terrestrial environment? Say we have a planet with the same size and atmospheric density as Earth. The temperature at the point closest to the star is 70 degrees Celsius, and on the opposite side, it's minus 70 degrees. For the record, I chose minus 70 as the coldest temperature because carbon dioxide freezes at negative 78.5 degrees, so if we go lower, we risk atmospheric collapse. So, the average temperature on the light side is 35 degrees, and on the night side, it's negative 35 degrees. Every object in space will be losing heat energy as thermal radiation. The equation for the energy released as radiation is this. So, how much heat energy on the dark side will be released into space as radiation? Well, the radius of the Earth is 6.371 million meters, so the area of the dark side, if it was orbiting a red dwarf, would be 2.55 times 10 to the 14 square meters. At negative 35 degrees Celsius, or 238 Kelvin, the total energy released as light will be 4.64 times 10 to the 16th watts. On the Earth, the planetary rotation keeps heat evenly distributed between the eastern and western hemispheres. On a tidally locked planet, heat lost as thermal radiation on the night side has to be replaced by air coming in from the day side. Since the Earth's rotational speed is 463 meters per second at the equator and 328 meters per second at 45 degrees latitude, if the atmosphere of a tidally locked world is to be kept stable, tornado-force winds would have to cover most of the planet. There are some ways that this could be mitigated. For example, if there is a strong greenhouse effect, more of the outgoing radiation from the night side will be absorbed by the atmosphere. This means less heat energy, and thus less air mass, has to be cycled between the day and night side. Earth's atmosphere absorbs 39% of the outgoing radiation, but a greenhouse effect which could absorb 85% of the radiation is realizable with high concentrations of methane and nitrous oxide, both of which are byproducts of microbial metabolism. Also, given that water has a much higher heat capacity and density than air, ocean currents could aid in delivering heat from the day to night side. However, it will still have to be transferred by air from the oceans to the continents. The larger the area of a continent on the dark side, the more energy it will lose as thermal radiation, increasing the total air mass that has to flow from the ocean to the continent, and thus increasing the wind speeds. The greater the coast length of the continent, the more this airflow will be spread out, and thus the lower the wind speed. Since area is a function of pi r squared, while circumference is a function of 2 pi r, as the radius of a continent increases, the area will increase faster than the circumference will. So, larger continents would be subjected to harsher winds. Although, having an irregular shape could increase the coast length without necessarily increasing the area. Since the heat energy that the continents on the day side get from the sun has to be transported to the night side, they would also face harsh winds, which would make small islands more hospitable. But ultimately, combinations of the greenhouse effect and ocean circulation could bring the wind speeds down from tornado force to gale force, harsh but still habitable. But how could life cope with this should it venture out onto land? Well, first looking at the photosynthetic organisms on Earth, they make support structures made out of cellulose. But to cope with the high winds, those on an M-dwarf planet could instead secrete a mineralized support structure. This can be thought of as a terrestrial version of corals, where instead of polyps sticking out of the mineralized part, they would have the aforementioned UV protective flower-like structures with a network of stolen analogs connecting the photosynthetic structures in the colony. Furthermore, one thing that would make the winds more manageable than those of the same speed on Earth would be that those on a tidally locked planet would mostly flow from one direction, with a few degree offset variability. This would mean that any support structure would only have to be reinforced on the axis running parallel to the airflow. Since the surface wind would be blowing in from the night side, the reinforced part of a support structure would be on the side not facing the sun and thus wouldn't impede photosynthesis. As such, instead of forests, photosynthetic organisms on tidally locked worlds could form vast land reefs. Of course, we have to consider the possibility that the UV flares could prevent photosynthesis from evolving, or at least stop photosynthetic organisms from colonizing the land. If this is the case, the first pioneering terrestrial primary producers could instead utilize chemosynthesis. In the atmosphere, there are trace amounts of methane, hydrogen, and carbon monoxide, which microorganisms can oxidize as an energy source. For more info on that, you can see the video, Living Off Thin Air, Microbial Trace Gas Oxidation. Microorganisms which live off these trace gases could form biofilms on shaded parts of the shoreline. Instead of being a hindrance to these organisms, the high winds could act as an asset, blowing their metabolites across the biofilm, allowing them to take up trace gases at a much greater rate than they could do here on Earth. The aforementioned trace gases yield the following energy when oxidized, and are present in the atmosphere in the following concentrations. This means that if a mole of air was metabolized, 1.76 joules of energy would be yielded. Since the average molecular weight of air is 28.96 grams per mole, and each cubic meter of air has 1,225 grams, there will be 42.3 moles per cubic meter. This comes out to 74.5 joules per cubic meter of air. If the wind is blowing at 50 meters per second, there is a maximum theoretical power yield of 3,723 watts per square meter. For comparison, when the sun is directly overhead of you, a square meter will receive 1,360 watts of light energy. Of course, it's completely unrealistic to expect that all of the trace gases could be absorbed by the microbes. However, photosynthesis isn't perfectly efficient either. Roughly 6% of the light energy hitting a plant can be used, while the conversion of chemical to cellular energy is 50% efficient. Furthermore, it takes about 525 kilojoules of energy to assemble 1 mole of organic carbon into biomass, while it takes 515 kilojoules to reduce 1 mole of carbon dioxide to formaldehyde, which is roughly in the same redox state as biomass, using water as the electron donor. So half the energy used by a photosynthetic organism would be used to produce organic carbon from carbon dioxide, while the other half would be used to assemble these organic molecules into biomolecules. Meanwhile, the trace gases are already reduced, so a trace gas oxidizer could use all the energy it obtains from metabolism and macromolecular assembly versus carbon fixation. You might also be asking, if photosynthesis is inhibited, won't that mean there would be less oxygen, limiting trace gas oxidation? Well, actually, it would benefit it. Abiotic reactions in the atmosphere slowly oxidize methane, hydrogen, and carbon monoxide. The current concentrations of these species in the atmosphere are known as the steady state concentrations, where they are produced at the same rate that they are oxidized. Since the rate of abiotic oxidation is going to be the product of the concentration of the trace gas, some constant K, and the oxygen in the atmosphere, if the concentration of oxygen is decreased, the concentration of the trace gas would increase until a new steady state is reached. For example, if the concentration in the atmosphere of a red dwarf version of Earth is 2% versus 20%, the concentration of methane would go from 1.8 to 18 parts per million, or 0.0018%, less than 1/1000th the concentration of oxygen. Now, there are other factors involved. For example, with less photosynthesis, there will be less organic carbon produced to be broken down into methane. But with less oxygen, a greater portion of the organic carbon will be broken down versus oxidized. So, will methane production rates on such a planet be greater or lower than here on Earth? I would wager higher, but I'll leave that up to the world builders to decide. Either way, you'll have greater concentrations of trace gases, while oxygen is nowhere near limiting, increasing the chemical energy available to organisms which metabolize them. But what if there's no oxygen available? Still not much of a problem. Hydrogen can be reacted with carbon dioxide producing methane. This reaction yields 131 kilojoules of energy per mole of methane produced, or about 33 kilojoules per mole of hydrogen metabolized. So if you go back to our earlier calculations, we figured that the trace gases give 1 mole of air 1.76 joules. So if oxidizing hydrogen using carbon dioxide as the electron acceptor gives you 33 kilojoules per mole, you would need a hydrogen concentration of 53.3 parts per million to get the same energy yield from the air that you would now. On a planet without oxygen, concentrations of hydrogen this high or greater would be commonplace. On Earth, photosynthetic microorganisms formed structures in the shallows known as stromatolites billions of years ago. On our hypothetical planet, chemosynthetic trace gas oxidizers could instead form similar structures. They can then alter their shapes to be more efficient at absorbing metabolites from the air by forming ridges running parallel to the airflow. Later, some could then evolve secondary ridges running along the original ones to further increase the area over which trace gases could be absorbed. As these organisms colonized the land and evolved multicellularity, they could form wind reefs powered by chemosynthesis. So far, we've discussed this chemosynthetically powered terrestrial biosphere is an alternative to one powered by photosynthesis, but they're hardly mutually exclusive. Since half the planet is in perpetual light and the other half in darkness, you could have the land reefs on the illuminated side and the wind reefs on the dark side, or at least the parts not subjected to permanently freezing temperatures. So now we've discussed what the primary producers on such a world would be like. What about the consumers? Well, for one, everything we know about comparative physiology seems to indicate that high levels of oxygen are needed for animal-like organisms to evolve. If oxygen can't build up in the atmosphere for the aforementioned reasons, would this prevent animal-like organisms from evolving altogether? Well, not necessarily, but they would have to take a very different evolutionary trajectory. Now, this is a bit of an oversimplification, but first a single-celled flagellated organism began sticking together. These cells then formed the inside lining of sponges. These then evolved into polyp-like animals, then something like a worm, and then animals like fish and crustaceans, whose descendants then crawled out of the water onto dry land. However, on a planet with limited photosynthesis, the concentration of dissolved oxygen would be too low to facilitate such organisms. The key word here is dissolved oxygen, because the Henry's law constant for oxygen is 1.4 times 10 to the minus 3 moles per atmosphere, meaning there will be 1.4 millimoles per liter of oxygen dissolved in water in an atmosphere with pure oxygen at sea level. If we apply the ideal gas law, we get that there will be 41 millimoles of oxygen in 1 liter of air, or 29 times as much in the same volume of water. With all photosynthesis occurring in the water, one could argue that the oceans would be supersaturated with oxygen, but with intense wave action and high rates of oceanic circulation, it will quickly equilibrate with the atmosphere, leaving the ocean suboxic. This means that instead of evolving in the water, animal-like organisms could instead evolve on land from something like a slime mold, which would then give rise to simple animals such as the ones we see in the Ediacaran, before evolving into ones with metabolic rates on par with modern marine invertebrates, essentially a terrestrial Cambrian explosion. Of course, this wouldn't occur until primary producers came out onto land, giving the ancestors of animal-like organisms something to eat. These alien animals could then shelter themselves from the high winds by taking cover in naturally occurring craglands or in the land and wind reefs. With oxygen composing a few percent of an atmosphere as thick as Earth's, cold-blooded animal-like aliens could sustain their metabolic requirements. But could a warm-blooded alien evolve? Our lungs only absorb 20% of all the oxygen we breathe in, but there are ways we can increase this efficiency. For example, birds have a unidirectional respiratory system, where the air they inhale is sucked into air sacs in their posterior region. These then contract to push the air into their tubular lungs and then into their forward air sacs. The front air sacs then contract, expelling the waste gases such as carbon dioxide and water. This allows birds to fly, i.e., physically exert themselves, at altitudes we'd asphyxiate at. As efficient as the system is, there are ways it can be improved upon. For example, an animal could have two sacs in front and two in back. When one of the front sacs inflates, drawing in air, the other one contracts, passing air over the lungs into a posterior sac. Meanwhile, the other posterior sac contracts, expelling air from the previous breath. The sacs, exhaling or inhaling air, would be kept separate from the ones passing air over the lungs by valves. Another strategy aliens could employ is to use the wind in a manner reminiscent of lamniform sharks and whales. Creatures living in the craglands would live in the cracks in the rocks known as grikes. These would have large, streamlined heads with heavily built forelimbs ending in hook-like claws. In order to quote-unquote take a breath, these aliens climb the wall of the grike, sticking their head and shoulders into the windstream, and open their mouths wide. Large quantities of air are channeled into their mouths by the wind, where it passes over gill-like structures. Despite the low concentrations of atmospheric oxygen, the high wind speeds pass large quantities of it over their respiratory surface, where it's absorbed into their blood. Within their body tissues are high concentrations of oxygen-binding proteins, similar to myoglobin and hemoglobin. Once these proteins have become saturated, the alien would jump back down into the grikes and continue foraging. When it runs out of oxygen, the creature would stick its head out into the windstream and do it again. So, sticking its head out would be like a marine mammal surfacing for air while using the ram ventilation strategy employed by some sharks. We can call these aliens pterolamnids. Although animal-like aliens would initially be confined to sheltered environments, those living on solid substrates like rocks could use padded feet similar to that of a gecko to remain anchored to the ground in the high winds. These aliens would also likely need armor plating to protect them from debris. Other species could use a single muscular foot in a manner similar to that of a snail. They would also have to be covered by their shell, making them a terrestrial version of a limpet. One way to mitigate the impacts of the harsh winds is to grow large, making it harder to get blown away. If oxygen limitation is an issue on the planet, one strategy aliens could use is to evolve into something resembling a dinosaur-sized tortoise. On the front top portion of the shell, it would have a series of holes known as ram siphons. The intense winds blow into these siphons, where the air flows over a respiratory surface in a manner similar to the pterolamnids, to provide them with sufficient oxygen. The feet and leg joints can be angled out 45 degrees in the front and 135 degrees in the back. This would allow the aliens to more easily move about in any direction while keeping their ram siphons facing the wind. In this scenario, it would also be advantageous to have eyes on all sides so the alien could see where it's going. It could have two eyes on its head and three other smaller ones around its body. Speaking of eyes, how would the difference in illumination regimes shape an M-dwarf alien's vision? As mentioned before, the cooler the star, the lower the average wavelength of the photons emitted. The peak emission wavelength is given by the formula 0.0029 divided by the temperature. So here would be the peak emission wavelengths of red dwarf stars of various surface temperatures, compared with that of red and purple light along with the peak emission of the Sun. Pretty much all of them are in the near-infrared range. So, does that mean that the vision of aliens on an M-dwarf planet would be redshifted? Well, that depends. On land, this would likely be the case, but visible light will penetrate the furthest in water. That's why visible light is visible, i.e. the wavelengths our eyes use. So, any animal living in the water would likely have a visible spectrum similar to ours. Since less of this light is emitted by the star, the bottom of the photic zone of the oceans would exist at a shallower depth. Eyes are of course very sensitive organs, and being exposed to high wind and debris would pose a problem. One way to counter this would be to have a transparent eyelid or nictating membrane to protect the eyes. This would of course be subjected to abrasion, making it translucent then opaque. A workaround to this problem would be to have it continuously growing from the outside. When the animal blinks, its main eyelids would have a layer of sharpened mineralized tissue which could scrape off the abraded bits, keeping the third eyelid clear. Harsh winds are one thing, but how would the animal-like aliens protect themselves from the ultraviolet flares? Well, modeling experiments have shown that with oxygen in the atmosphere, and thus ozone shielding, the UV light intensity on the surface during a flare wouldn't be much greater than what the Earth experiences at sea level from the Sun. Now, I should note that this model was based on how much UV light DNA will absorb. So, while it shows that animal-like and chemosynthetic aliens wouldn't be impeded by UV flares, the same isn't necessarily true for any phototrophic organisms. Given the intense radiation on the day side and the freezing temperatures on the night side, the greatest biodiversity on a red dwarf planet would likely exist around the day-night terminator. We can call the area to the immediate day side of the terminator the dusk zone, and the part immediately to the night side the twilight zone. Perpetual night wouldn't start immediately past the day-night terminator, because some of the light would be refracted by the atmosphere, giving us the twilight zone. Animal-like aliens in the dusk zone would probably have a visible spectrum redshifted the most, because the shorter wavelength photons will be scattered by the atmosphere as the starlight passes through it at an oblique angle. However, those in the twilight zone likely would have a visible spectrum centered around green light. These photons have a wavelength long enough to pass through the atmosphere, but short enough to have significant refraction, which is why we see a green flash right when the sun sets. It should be noted that even though the planet is tidally locked, it will still precess, which will cause the sun to occasionally peak over the horizon in the twilight zone. Furthermore, while weather patterns on a given part of this planet would be more constant than those on a specific location here on Earth, this precession, coupled with sudden changes in the luminosity of the star, can cause local variations in meteorological conditions. While so far we've discussed the accumulation of atmospheric oxygen in the context of photosynthesis, there are other means by which it can be produced. If the planet's dynamo shuts down, the atmosphere will be bombarded by high-energy protons and electrons. High in the atmosphere, these will split molecules of water vapor to form oxygen and hydrogen. Hydrogen, being the lighter element, will be more readily blown off into space by the intense solar wind, while the oxygen will remain. Mathematical modeling experiments have indicated that this can lead to oxygen concentrations 10 times what we have here on Earth. Of course, there is the issue that here on Earth, oxygen, carbon, and hydrogen are cycled in a biosphere driven by photosynthesis, i.e., it's contained on the planet. Meanwhile, on a planet with abiotic oxygen production, the hydrogen is being removed, meaning that eventually the water will run out. But how long will this take? Well, 1.2 times 10 to the 14th kilograms of carbon dioxide are fixed every year by photosynthesis. And since photosynthesis will produce 1 mole of oxygen for every mole of carbon dioxide consumed, when we adjust for the difference in molecular weight, we get that 9.14 times 10 to the 13th kilograms of oxygen are produced per year, roughly 0.85% of the total mass of oxygen in the atmosphere. Since the oxygen concentration is in a steady state, this much is consumed by heterotrophs every year. So, How quickly would abiotic oxygen production deplete the water on Earth? First, even though two water molecules are needed to produce one oxygen molecule, when the oxygen is used as an electron acceptor in the oxidation of another chemical, be it organic carbon, sulfite, ammonia, or something else, usually one of the oxygen atoms will be incorporated into a water molecule, replenishing the original, so the stoichiometry is effectively 1 to 1. When we adjust for the differences in molecular weight between oxygen and water, we get 5.14 times 10 to the 13th kilograms of water will be lost, and given that the oceans have 1.43 times 10 to the 21st kilos, abiotic oxygen production at current consumption rates would deplete the oceans in 27.8 million years. Given that the Phanerozoic eon spanned 541 million years and counting, this isn't much time for complex ecosystems with animal-like aliens to evolve. However, not all of the Earth's water is on the surface. Estimates vary as to how much water is in the mantle, but it may hold as much as 5 times that of the oceans, with some estimates giving tens of times. On top of that, due to the proximity of the planet to the Sun, tidal heating would increase volcanic activity, getting more of this water out into the atmosphere. This would extend the lifespan of oxygen on a hypothetical Earth-like planet orbiting a red dwarf to 167 million years. For some perspective, our ancestors crawled out onto land some 160 million years after the Cambrian explosion kicked off the Age of Animals. So, complex ecosystems could evolve on such a world, but probably wouldn't reach the level of diversity we see now. So far, I've assumed a similar rate of oxygen consumption to what we have here on the contemporary Earth. But on our planet, one side would be frozen, which would heavily curtail total global metabolic activity. Furthermore, if enough radiation was striking the atmosphere to produce oxygen at a similar rate to photosynthesis on Earth, it would, in all likelihood, render most of the day side barren. As such, the only place Earth-like ecosystems could form would be on the day-night terminator, limiting global oxygen consumption rates to a fraction of what we see here on Earth. If, say, the biosphere consumed 1/20th of the oxygen that the biosphere on Earth consumes, there would only have to be 1/20th the oxygen production, and by implication water consumption, right? Well, not exactly. If all life on Earth ceased, within about a million years, the oxygen would be depleted by oxidizing minerals in the crust. About 2% of the oxygen on Earth that is consumed is taken out of the atmosphere by this oxidative weathering. But on our red dwarf planet, it would be more than this because the greater volcanic activity will bring more reduced minerals to the surface. Furthermore, since these minerals usually don't have hydrogen atoms in them, the oxidative weathering won't regenerate water molecules that were split to form oxygen. So, let's say oxidative weathering occurs at a rate 2.5 times that of what we see on Earth. If the global metabolic rate on our hypothetical planet is 1/20th that of Earth's, total gross oxygen consumption will be 1/10th that of what occurs on Earth. This would be evenly split between biotic and abiotic processes, while maintaining a similar steady state concentration to what we see on Earth. When we adjust for the lack of replenishment by abiotic weathering, the oxygen and water would last 1.1 billion years, plenty of time for complex macroscopic life to evolve in a manner similar to Earth. The day-night terminator region where most life exists wouldn't get nearly enough light to sustain an ecosystem driven by photosynthesis. Instead, primary producers could react reduced volcanic gases coming up from the ground with abiotically produced oxygen. The chemosynthetic plant-like aliens would again secrete a lithified shell to stay anchored to the ground amidst the high winds, again forming reef-like structures. But instead of having fin-like structures to capture as much gases out of the atmosphere like the wind reefs, they would instead have roots that extend into the ground. The roots would absorb volcanic gases such as hydrogen sulfide, where they'd be reacted with oxygen. Although hydrogen sulfide is gaseous, the product of its oxidation, i.e. sulfate, is a solid. This might pose a problem for waste accumulation. Marine chemosynthetic organisms release it into the surrounding solution. Instead, these terrestrial chemotrophs can grow gypsum crystals out of their top, so the sulfate gets blown away by the wind. So, just as deep-sea hydrothermal vent organisms react volcanic gases with oxygen produced in the photic zone, in the twilight zone of the hypothetical planet, organisms oxidize volcanic gases using abiotically produced oxygen from the day side. These chemotrophic organisms can form a third type of reef, i.e., gas reefs, over volcanic upwellings, which could in turn host animal like alien life. Although chemotrophy would be the main process driving primary productivity, there could still be photosynthesis on such a world. In the twilight zone of Earth's oceans, red algae photosynthesize at depths of over 200 meters. Similarly, lichen or moss-like organisms on the red dwarf planet could grow on the side of the mountains facing the substellar point in the twilight zone. Here, they would be shielded from the winds blowing in from the night side and use the light refracted by the atmosphere to carry out photosynthesis. Although all red dwarfs that are alive today are flare stars, when any star is at an earlier stage in its life cycle, it will also be a flare star. Red dwarf stars are incredibly long-lived, with smaller ones capable of carrying out fusion for over 1 trillion years. So, the universe hasn't existed long enough for red dwarfs to get out of this flare stage. A few tens of billions of years down the road, red dwarfs will become far more stable and thus hospitable. If flare activity prevents red dwarfs from being habitable now, they can be far more ideal for life in the future. Even if they de-atmosphere the planets which formed around them, red dwarfs can still capture rogue planets, which would then become habitable. Once the star-forming, or stelliferous era ends, long-shining red dwarfs can provide life with an oasis in the cosmos. Also, since ice absorbs most infrared light while reflecting most visible light, it's far less likely that a runaway cooling effect will cause a snowball Earth on a planet orbiting a red dwarf star. But, say a biosphere did evolve on a red dwarf before its flare stage ended, how would it respond to this change? For one, photosynthesis wouldn't be as limited, allowing oxygen levels to increase. As a result, it would be easier for endothermic metabolisms to evolve, or at least they wouldn't have to rely on ram ventilation. The oceans could also have had enough dissolved oxygen to support fish-like organisms. So, you could have had the reverse of what you had on the Earth between 420 and 360 million years ago. These early marine pioneers would likely initially maintain their lungs and put off evolving gills, taking advantage of the ample oxygen in the air. But as some evolved a benthic lifestyle, or lived in deeper depths, there would be stronger selective pressures to evolve gills and then lose their lungs. Although, those that lived close to the surface would probably keep their lungs. So, that's it for red dwarfs. But could even cooler stars, i.e. brown dwarfs, support alien life? Brown dwarfs are stellar bodies too small to fuse hydrogen, although the larger ones can fuse deuterium. These range in mass from 13 to 80 times that of Jupiter. However, they usually have roughly the same radius as Jupiter, i.e. as their mass increases, their density instead of volume increases. Brown dwarfs have three spectral classes, which go L, T, and Y from hottest to coolest. The cutoff between L and T class brown dwarfs is 1200 degrees Kelvin, and 600 Kelvin divides the T and Y classes. Meanwhile, 2300 Kelvin is the cutoff between the red dwarfs and brown dwarfs, while 500 Kelvin divides brown dwarfs from rogue gas giants. Well, first things first, if the planet orbited the brown dwarf closely enough, tidal heating would produce a subsurface liquid ocean. Furthermore, simulations have shown that if the planet had a sufficiently thick hydrogen atmosphere, it could induce a sufficient greenhouse effect to support liquid water on the surface. But this atmosphere might not even be necessary. The formula for tidal heating is as follows. One planetary body in the solar system, which is renowned for being subjected to tidal heating, is Jupiter's moon Io, with towering volcanic plumes. But let's say Io was orbiting a brown dwarf 50 times the mass of Jupiter. How far out would it have to orbit to be subjected to the same tidal heating? A is the orbital radius of the satellite from its parent body. Since Io's orbital radius is 4.22 times 10 to the 8th meters, for a planetary body to experience the same tidal heating effects, it it would have to have an orbital radius of 1.55 times 10 to the ninth meters, 3.68 times that of Io. But let's say that instead of Io-sized, this planetary body was Earth-sized. What would it be like? Well, if we look at the equation, tidal heating is a function of the radius to the power of 5. Since the flux is spread out across an increasing surface area, if the radius of the planetary body is increased, the heat flux per square meter will go up by the power of 3. The geothermal heat flux of Io is about 2.5 watts per square meter. If we multiply this by the quotient of the radius of the Earth and that of Io, we get a geothermal heat flux of 107 watts per square meter. If the brown dwarf parent body has the same volume as Jupiter and is a borderline TL class stellar body, its total light output will be 7.22 times 10 to the 21st watts. At the distance that the hypothetical planet orbits, it will receive an average of 59.4 watts per square meter. With this much energy being input into the surface, the greenhouse gases in the planet's atmosphere would have to absorb 57% of the outgoing infrared radiation in order to maintain a surface temperature of 288 Kelvin, which is the average surface temperature of the Earth. And this is not too much more than the 39% that the greenhouse gases in Earth's atmosphere absorbs. But what kind of life could such a planet support? Well, for one, this planet would be volcanically active, and high-temperature volcanoes emit oxidized gases, while low-temperature hydrothermal systems emit reduced gases. So, if organisms lived around a vent, they can oxidize reduced gases emitted by the vent, using atmospheric gases as the electron acceptor. Although, without oxygen, the communities wouldn't be anywhere near as complex as the ones which exist around hydrothermal vents on Earth. But could the light from the brown dwarf be utilized? It is true that the intensity of PAR on such a cool star would be too low to support photosynthesis as we understand it. But light could be used for other purposes besides photooxidation. Instead of taking up water and carbon dioxide to produce glucose, phototrophic organisms here can take methane and carbon dioxide to produce acetic acid, which is then assimilated into their biomass. This reaction will require 54 kilojoules per mole, meaning that 9 times 10 to the minus 20 joules will be required to produce one acetic acid molecule. Since the energy of a photon is the Planck's constant multiplied by the speed of light divided by the wavelength, a photon with a wavelength of 2,217 nanometers will have enough energy to power this reaction. On top of being used to drive the production of organic molecules, light energy can be used to power metabolism in a process known as photoheterotrophy. If the aliens living on this planet have a biochemistry powered by phosphate hydrolysis like ours, adding a phosphate group to a polyphosphate energy-carrying molecule, i.e. their version of ATP, will require 30.5 kilojoules per mole. Since there's a directly proportional relationship between wavelength and energy, a photon would have to have a wavelength of 3,925 nanometers to facilitate this reaction. At 1200 degrees Kelvin, the peak emission wavelength of the brown dwarf will be 2,417 nanometers, so there would be plenty of photons with enough energy to drive both of these reactions. One major limitation of this metabolism is that since water absorbs in the infrared, it would most likely have to evolve once microorganisms began crawling out onto the land. These could then evolve into multicellular, methanotrophic plant-like aliens. Okay, so without oxygen, we know that animal-like life couldn't evolve, but could there be forests of photomethanotrophic tree-like organisms? My tentative answer would be no, because even though we think of the plant life in forests, or any terrestrial system, as supporting the animal life, in reality, it's an interdependent web. Animals, and other oxygen-using organisms such as fungi, carry out many functions such as breaking down dead organic matter, transporting nutrients, and treating the soil, which allows plants to form complex communities such as forests. So maybe the methanotrophic plant-like aliens could form communities on par with those that land plants formed on the Earth between 450 and 400 million years ago, with low-growing coastal marshes and a few fields. But that's probably the maximum complexity you're going to get in a planet orbiting a brown dwarf. In summary, life on planets orbiting red dwarf stars would face many harsh but not insurmountable challenges, such as UV flares and intense winds. In fact, organisms could potentially turn the high winds to their advantage, using them to take up trace gases to be metabolized, or ram ventilate, allowing them to take up sufficient oxygen, given that its concentration will be low, with photosynthesis limited by UV flares and the low levels of PAR. Even though they may seem inhospitable now, billions or trillions of years in the future, red dwarf systems may be an oasis of life. Hey everyone, I would like to use this outro to do a bit of an addendum. In my Living Off Thin Air video, I said there was 0.0094 moles per liter of air, but that's how much oxygen there is in 1 liter of air. There's 0.0448 moles of molecules in 1 liter of air. So based off that mistake, I said it would take the hydrogen and 13,128 cubic meters of air to produce 1 gram of organic carbon, 26,256 cubic meters to produce 1 gram of biomass, and 1 liter of air could produce 126,960 E. coli sized cells. When we correct for the mistake, we find that it would take the hydrogen in 2,756 cubic meters to produce 1 gram of organic matter, 5,514 cubic meters to produce 1 gram of biomass, and 1 liter could produce 604,571 cells. I also said that if we were methanotrophs breathing at the rate we normally do in an atmosphere of 5% methane, we can sustain a metabolic rate of 8.37 watts, and if we breathe heavy, it could be 139 watts. Instead, it would be 39.9 and 662 watts respectively. What change does this have on the key takeaway? Well, with our normal breathing rate, we couldn't sustain our basal metabolic rate of 121 watts either way. But if we breathe as heavy as we do when carrying out intense exercise, an atmosphere made of 1% methane could cut it, versus something dangerously close to the levels where methane becomes flammable.